Greg, welcome to the Astroben podcast. How are you?
I'm doing well, thank you. How are you doing, Ben?
I'm very good. I'm very good. I'm excited to talk to you. I don't think I've ever understood what a guest does less than you, to be honest, and I mean that in the nicest possible way. So let's start with your company. So the ZC Institute or the ZC Institute, being a US based. What on
hmm
earth is it?
ZC Institute, and the ZC actually stands for zero carbon. And what we're actually doing is we are using, in essence, we're cheating physics. We're using a nice little quirk in physics um, to work on microscopic or nanoscopic space-time distortion technology, which will allow us to create sustainable nuclear fusion. And there's a lot of, and I'm not going to go into any of the math because I don't want anyone to just have an aneurysm or die or anything of that nature when they're listening to your podcast. But in essence, there is a way to create very, very small space-time distortions that will allow us to create the conditions needed for sustainable nuclear fusion, which is what we're looking at right now. Fusion is a big thing. It's the holy grail of energy, right? Every single renewable energy resource has a disadvantage. So solar power, you have to build the panels, of course, and the sun goes away at night, and it never tells us where it goes. When it comes to wind, it only works when the wind's blowing. Hydroelectric power, there's a lot of environmental degradation, a lot of environmental issues with that. In fact, the example I always use is the Aswan High Dam. The Nile is flooded for thousands of years. It doesn't flood anymore. That's great, except for now there's no silt being deposited, which means now you have agricultural degradation when it comes to being able to plant. So Egypt isn't growing as much as it used to anymore. So everything's got a problem. Even nuclear fission has a problem. I believe that the UK is starting up Sizemore C again, or something to that effect, which is a nuclear reactor. I forget exactly where it is in the UK, but they're trying to get nuclear reactors up and running. But the problem is that you're still producing radioactive waste. You still might have a chance of a meltdown. Everything's got a problem. Fusion, on the other hand, is the byproducts are going to be helium gas and electron flow and energy. And we know it works because you can step outside, maybe not in London because of all the fog and clouds and whatnot, but you can step outside and look up and there's the sun. And it does work. So we know it's there. We just don't know how to do it on the planet, but we think we have a nice way to cheat the system to actually make it work the way that we want to.
And how would that work? I understand it's all theoretical at the moment, but is this an experimental thing that we could actually do? And is it dangerous? Because it sounds like you kind of want to make a mini sun.
A very mini sun. In fact, actually, if you don't mind, I'm going to share my screen and actually present, if I can. There we go here. Show that, and do that. And then we're going to go ahead and from the current slide. Very good.
For those listening audio only, I'll put a link to this file in the show notes as well.
So the idea was, one of the issues we have, of course, from nuclear fusion is that everyone's using what we call a brute force approach. There's two main ways that that companies or governments are trying to do fusion. One is it's the tokamak reaction, which is you put everything into a magnetic bottle, you spin it around very, very fast, and you put your reactants in, and they smash into each other, and that's where you get your fusion. Fusion is kind of weird. You're trying to put atomic nuclei together. The issue is atomic nuclei hate each other. Positive forces want to repel each other. So you have to get them close enough and hot enough where they get close enough where the strong force takes over for them to grab them. So we have a brute force approach. With the tokamak, you spin it up really fast, you put your stuff in, things smash into each other, you get energy. Or you do what Lawrence Livermore did, which is called inertial confinement. You take a bunch of lasers, you fire it to a very small pellet of these isotopes, deuterium and tritium, and once you fire that, that's going to create the fusion or start this fusion, and then you're going to generate power. But the problem is you got to put more and more power to do this, and a lot of the power is being wasted. You're not actually going anywhere. So we thought, okay, well, what can we do? Turns out that you can actually distort space-time. We're doing it right now. We're sitting in what's called a gravity well. If you imagine that if you imagine a trampoline, if you put a big, massive bowling ball in the center, the trampoline kind of dips down, right? When you think about that, roll a marble by that big bowling ball, and you'll realize that the marble doesn't go straight. The marble kind of curves a little bit. That's what space-time is. Mass distorts space-time. So does energy. So we know that space-time can be distorted. We're sitting in it right now. But no one thought about making it very, very small. So our idea was, why don't we go ahead and make this very, very tiny, very, very small space-time distortion? We're talking about angstroms or nanometers. And the idea for us right now is we're working with several researchers to actually do this in the lab. The energy calculations show us that we can do it in the lab. It's not something that you can do with 2 car batteries and some wires, but you can do it in the lab. And once we show that, and I'm going to skip this for right now, there's a way to actually pulse it. You can turn the warp field on and off, the space-time distortion field on and off. So in essence, in this nice little piece, you see like the blue is where you stuff the energy that you're using or the mass that you need. A warp field, or how you warp space-time, all you need is a very thin, dense field, or a very thin, dense section of mass or energy, or both. That's all you need. So the blue part is where you put that stuff. Maybe it's electrons, or maybe it's protons, or maybe it's energy, some sort of electromagnetic energy, something to that effect, and you create a containment field around it. The nice thing is, to cut it off, all I have to do is make the warp field, expand the warp field, because the density is what matters. Remember, I said it has to be very, very dense. So if I just expand it, everything kind of goes out, and that means you're not creating the warp field. But that also means I'm not draining it. So I get something like this. So I can turn it on and off, which means I can control the flow of whatever's going in, whatever's coming out. And because of that, this is what we get. If you create, and this, again, we're taking our best guess as of right now, given the theoretical simulations and the computational simulations we're doing. But if you take 4 of these microscopic space-time distortions and you turn them all on at the same time, the blue piece is where you put everything in. When they all get turned on, that blue piece, and you'll notice in this nice little graphic, is getting crunched. It's actually becoming less volume. If you put a high number of atomic nuclei in there, in essence, you're folding space-time on itself, or you're crunching space-time, which means that those nuclei are basically being folded on top of each other. That's the trick. And that's where it gets really fun. For us, that actually means that we might be able to do nuclear fusion on a very small scale, like the size of a table. And now we can produce terawatts of power. All we need to do is make sure we're sending in the right isotope. So deuterium, or maybe helium-3, might be protium. We're not sure yet. But that's what we're doing right now. Right now, phase 1 is our proof of concept. We're actually working with 3 researchers with labs, and we're actually looking to add 2 more on. And each of them each of them has a piece that they're actually that adds to the whole gestalt. One of them is doing experimental work, one of them is doing fusion work, one of them is doing computational calculations, and each of them kind of reinforces each other. When we show proof of concept, which by the way I'm hoping we'll have soon, the lab that's doing the experimental work is waiting on literally one piece of equipment to plug in, and then he can start his experiments again. Once we show that, we can begin working on building these fusion reactors. It'll be about 10 years. But that's a lot better than everybody else is right now. So we're kind of excited about that. And I kind of went off for a bit, so I know you have like 20,000 questions, so go for
it. No, it's fascinating. So I was trying to follow what the actual process is. So let's start with faster than light, that whole sort of concept. And is this a faster than light warp drive? And what are the challenges with theorizing this?
All right, so I hear you, because of course whenever someone hears warp drive, they think about this, right? That's what everyone kind of goes to. They think, oh, you're trying to build the Enterprise. The answer is yes, but that's way down the road. We don't want to do faster than light. We don't want to do FTL anytime soon. There's 2 types of warp bubbles. One is a symmetric warp bubble. When I turn it on, it contracts or expands space-time all the way around it, the same way. It doesn't move, because I don't want a reactor that, when I turn it on, it shoots off somewhere and does something random, right? I want it to stay in the same place. Symmetric warp bubbles take less energy than asymmetric. Asymmetric is the Star Trek stuff. That is, you're contracting in the front and you're expanding in the back. That is how you start moving things. But really, we have to remember that you're not actually moving. The universe is moving around you. And that's what people kind of forget sometimes. Yes, there's a lot of challenges with respect to FTL. We're not worried about that right now. We're trying to actually just create a warp bubble in general to show that we can distort space-time. We don't want to go FTL anytime soon. FTL is going to require a large amount of power, and we don't really fully understand what it's going to do when we turn it on. However, sublight is fine. If I'm doing a tenth the speed of light, we still beat everybody else out of the court without a question. Imagine being able to, and because this is, you're in Britain, I'm going to go ahead and use this wonderful example. In fact, you guys will get a kick out of this. Let's see. I'm going to share the screen one more time, and you'll see exactly what I'm talking about. No. Let's go ahead and get that back up. Hold on. There we go. Let's go ahead and share that. So the idea is, I'm going to skip over some of this stuff. The idea is that once we had that fusion power, now I can begin constructing sublight ships. Something like this.
And it's a TARDIS for people listening.
It is indeed. It is a TARDIS, yes. And the thing is that we can actually build something similar to it. The idea would be you get into the police box and you have the conversation with the TARDIS, and you say, listen, I want to go to Nairobi. And the TARDIS says, what address do you use? And you give it the address. And 4 seconds later, you step out of the police box and you're in Nairobi. And the reason is, and this is where it gets, again, quite fun for us, the idea is that we're not trying to warp this massive amount of space-time. The more you warp space-time, the more energy you need. So why don't we just do a micrometer at a time, but we do it 100 million times a second? That's why we needed to pulse the drive. That means I don't need an airport to launch from. That means I don't need a seaport or something of that nature. I can launch from my driveway. I can launch off of grass and not hurt the grass. And I'm literally just taking a curve and going up and coming back down again. But you're not going to feel the acceleration at all. It's a non-inertial drive. You land, and again, you step out in Nairobi in 4 seconds. But to do that, I need a lot of power, a great deal of power. That's why you have to have the fusion reactors first, right? I can't do it otherwise. Because fusion is one of the few power sources that gives us what we need. It's fusion, fission, and matter-antimatter reactions, which is what Star Trek uses to actually run their warp drives. Fusion might get it done, though. So when we do discuss FTL, yes, we are looking to do that, but that's going to be, I might be dead by that point. The goal is that once we do the proof of concept, we create the fusion reactors with that proof of concept. In essence, we're doing creating it once is great. Now I got to create 4 of them and have them turn it on and off at the exact same time. There's a lot of timing issues, technical issues, and engineering issues. That doesn't mean it's impossible, but that's going to take several years to do that. But once we do that, now I've got the power requirements to begin making the field bigger. Now I'm doing a micrometer field or a millimeter or a centimeter. And each time that we make it bigger, we can learn more about the field itself and how it works. Once we get to a meter or 10 meters, hey, 10 meters, that's a TARDIS. And at that point, now we can start flying people around. 100 meters, that's, there you go. I don't want to go faster than the speed of light anytime soon. I want to do 1/3 the speed of light. If that's the case, I can still be on Mars in 10 minutes. That's huge. And that's
it definitely sounds like science fiction. It's pretty mind-blowing.
Well, that's the interesting thing. It sounds like science fiction. But the thing is, we're not breaking any physics rules. There's nothing that says you can't distort space-time. It happens all the time. It's an integral part of Einstein's equations. Relativity clearly shows that you can distort space-time with a large amount of mass or energy. But we're not using a ton of mass or energy. We don't need to create this massive distortion. You just need to create this little tiny distortion. And that drops the energy requirements to a place where you can actually do it in the lab.
But based on our current understanding of physics, what needs to be solved? Is it something to do with the strong force and the weak force and how everything all interlinks? Like what big discoveries do we need to hack before this becomes more than a sort of theoretical exercise?
So you're diving into some of the technical fun stuff. So now we do have to do a little bit of the math. The answer is, when you look at Einstein's equations of relativity, there's a way to create what's called a shaping function. And the shaping function is what distribution of matter and or energy you would need to create a warping field. And we've done the calculations for that. In fact, since 1994, when the first warp drive paper was published, it's been a huge intellectual exercise of people kind of sitting down and figuring out how to do these things. And the problem is that to warp space-time, you require 10 times the mass energy of the universe to do what you want to do. That's a problem. By the 2020 or so, 2019, 2020, the calculations dropped to about the mass energy of Jupiter. So we've gone from a unicorn to a small vial of unicorn blood. It's still impossible, but it's much less impossible. So my team sat down and we kind of looked through the numbers and we realized, one, everyone was saying the warp field to R equals 100 meters. Again, they're trying to build the Enterprise. A nanometer is 10 to the negative 12th meters. So that means we can shave 14 zeros off the amount of energy required, just off the bat, right? Secondly, they're trying to warp this massive amount of space-time to create FTL travel. Well, I don't need that either. Congratulations, we've shaved several more zeros off the amount of energy that we need. So right now, it's more of a technical and engineering challenge. How much energy do we need to actually, how are we going to create the shaping function? What kind of distribution of matter and energy do we need inside that little bubble that I showed you to get the job done? Now, the good news is Dr. Chance Glenn has actually done a great deal of research on this, and he's actually found a couple of materials that might work for it, and I'm not making this up. One of them is ethylene glycol. For those of you who do not know, it's antifreeze.
What?
Right, I know. Yeah, believe me, I was in the same boat. I'm like, what? And after looking at the math, I'm like, oh, okay. One of the issues with the shaping function is the fact that in the front of the shaping function is this big, massive negative. So a lot of the research that came out of it was we need negative energy or negative matter to do this, right? Well, we can't really do that. We don't have any way to create negative energy or negative matter. We don't even know if it's physically possible. We think it's theoretically possible. We've never actually seen it. Maybe with the Casimir effect, but we don't really have a way as a civilization to produce that. However, Dr. Glenn, with his research, has realized that, long story short, certain compounds have a complex dielectric constant that's higher than the real dielectric constant. Complex dielectric constant, of course, is a negative number. What happens when you multiply a negative times a negative? Oh, you get a positive. All of a sudden now you just need positive energy to make the thing work. So he actually has a setup in his lab. I was just at his lab, Friday, actually, in Texas. And he was showing me some things and whatnot and so on and so forth. In fact, I wonder if I've got a picture of it, I can actually see if I can pop it up real quickly. And you'll see what we're talking about. Because there's yeah, there we go. I'll do that one and I'll share this one because it's a lovely picture and I look like crap, but it's okay. Yeah. And so you'll see behind us, there's Dr. Glenn and there's myself wearing my Zephram Cochrane hat. You'll notice behind him, you see ethylene glycol and all that good stuff. The math shows, and you'll see up in the upper right-hand corner, the shaping function. That's what we're talking about. This is that very thin. This is the math required to figure out how to do it. So creating a very thin shell of high energy or high matter, and this ethylene glycol is kind of the key. In fact, he literally calls it warp plasma. The idea is if you pump enough energy into it, that will actually create frame dragging, which is a relativistic concept where you're actually distorting space-time just a little bit, and that's all we need to do. He's actually got an experimental setup ready to rock and roll on that. So to answer your question, the theory is sound. We know that the theory is set up and we know that what we need to do. The question is, are we able to actually do it in the lab? Which is why we're raising a large amount of money. Right now, what ZC Institute is doing, we're raising money to hand to labs. We want you to go ahead and do this stuff in the lab. So we're applying for National Science Foundation grants and NASA grants to actually help us do this. And we're also looking for private investment as well. The idea is we want to build our own lab, don't get me wrong, but we don't have the expertise as of yet to do this. So we're basically working with these people to actually get the proof of concept. We license the IP for them. They get partial ownership of the IP, and they also get equity in the company in exchange for giving us that. That's how we make our money. And then that money goes back into the research, and you get this nice little virtuous cycle. But it is not a theoretical issue. Theoretically, it is possible. We know it's possible. The question is, do we have the technological, engineering, and material science know-how to actually pull this off in the lab, and can we show it experimentally? And Dr. Glenn has set up a pretty decent experimental setup that I looked over. It'll get the job done. It's just a question of if we have our numbers right with respect to the amount of energy required, and we think we do. And again, this is not something that you can take 2 car batteries and call it a day. You're going to need to be able to plug into something not small. We're not talking about a couple of watts here. But just showing it, the joke is I usually discuss James Watt steam engine. James Watt steam engine, the first generation was a piece of crap. It just was. But it got the job done, right? But each generation is better and better and better. You get more efficient. And once we have the first generation, we can go back to our computational simulations, plug those in, and start fixing our numbers to figure out, if you turn this by 2 degrees, it's going to lead to a 10% energy decrease, or this will make it stronger, or so on and so forth. So we're all kind of waiting for the experimental data to come in so that we can plug that back in, and then again, you get that nice virtuous cycle coming back again. Ethylene glycol is the first solution, first compound that he's found, but more than likely, we can probably create or design metamaterials that will have a much higher complex dielectric constant, which will mean it'll be more efficient of what we're doing, to the best of our knowledge. And again, I could be wrong. You might want to pull Dr. Glenn on here to get more into the science, because I'm not I play a scientist in real life, but I'm not actually that kind of scientist. But I learned enough to kind of have these conversations.
Well, for someone that's not a scientist, you definitely seem to know what you're talking about. One term that I saw on the presentation that you flashed that I'd like to just question is the term quantum hack. How does distorting space-time on a quantum scale mean atoms can move without massive forces? I just can't conceptualize how that would work. And what is the quantum hack?
All right, so
apologies if you just explained it. And
no, totally fine. So I'm going to ask you a question, and I'm going to put you in the right frame of mind. Do you know what Bernoulli's principle is?
No.
Bernoulli's principle is a weird equation that basically says when air flows over basically like a wing, the air pressure is lower or higher in one part or the other. I can't remember exactly what it is, but in essence,
it meets it at the same point, the leading end as
right. And because the air pressure is different, you generate lift.
Yeah,
that's a quirk. That's a hack in the physics, isn't it?
I suppose it is. Yeah, and they only discovered that because some bright spark probably looked at a bump in a road and thought,
now,
imagine if a wing was shaped
right
like that.
Now imagine, that's really weird. That's such a random thing that happens. It's such a little quirk in physics, but you know what? You can build airplanes around that. So our idea is that when you have this, and like I showed you the quantum crucible, the quantum hack is when you turn all these things on, that volume gets much smaller, which means that in essence, the amount of space-time, the amount of volume itself has decreased, which means that where do the atoms have to go? In essence, they get folded on top of each other. They get folded on themselves. Not all of them and not perfectly. But that's the idea behind the quantum hack. You turn these things on, then all of a sudden, you kind of fold them on themselves. You get to, for lack of a better term, cheat. I'm a huge gamer. So if there's one thing I love, it's games with huge rule books. Why do you have the huge rule books? So people like me can read all 100 pages and go up to to someone and say, well, the rule book didn't say I couldn't do that. So why can't I do that? Well, I mean, because it doesn't, if it's not in the rule book, then I can do it. Well, I mean, yeah, cool. Physics is very much finding the rule book of the universe and figuring out where the loopholes are and figuring out where the places are. So when it comes to this, we believe, and again, because we're on such a small level, yes, you're absolutely right. It takes stupendous amounts of energy to fold over a table, right? But we're not doing that. We're using micrograms of hydrogen. So we don't need that much to really get this thing done. We don't need to fold this massive amount. We're folding something that you can't even see. It's literally microscopic. So because of that, we don't need as much energy to do that. And even better, think about almost like a 4-stroke engine, right? So you have those 4 little warp bubbles. One of them you cut off. That's your intake. So you put in your stuff, turn them all on. Everything gets crunched. So you have your compression phase. Then you have your ignition phase. Everything's close enough where you actually get fusion. And you have your exhaust phase. Because I haven't turned all of them off, because I don't have to keep refilling the warp bubbles, wash, rinse, repeat. And you keep getting more and more energy. Now, with that being said, to get it started, you're going to need a lot of power. So you're going to have a power deficit to begin with. But just like a car, you leave it running for a bit, and you can recharge the batteries, and then you just keep going, right? That's the idea behind it. And when I say quantum hack, the idea is there's nothing that says we can't fold space-time in the lab. There's nothing that says you can't do that. By folding space-time, we're literally taking these atoms and moving them closer to each other without moving them closer to each other. We're just decreasing the distance between them without moving them at all, if that makes sense.
I see.
It's weird because it kind of, sometimes when I talk to people, they're like, do you have any weed? And I'm like, I mean, yeah, it really helps to kind of like, sometimes a drug kind of helps because you're like, it breaks your mind because you're like, but you can't do that. Like you can't, but you can. And the usual thing I use, I say like, all right, so here's a piece of paper, and I have A and B, right? And the closest way to get there is between those 2 points is a line. unless you do that.
Mm.
And what we're doing is we're doing this several thousand times a second. So we're forcing it to keep coming together. We're not just like popping popcorn. We're not going to pop all the kernels, but because we've done it so often, we'll get the majority of them when we actually kick it out. That's the goal. It is bizarre when you think about it. And I'm saying this now with I want to put a caveat on there. Dr. Jason Casbury is who we're working with at the University of Alabama, Huntsville. He's the fusion engineer. And what he has been talking about is once we get the warp fields up, he's got a nice fusion software that basically he can put these numbers in and go, all right, here's the best way to set up. I'm saying 4. It might be a cube, might be 8, it might be 20. We don't know how many fields we're going to need. I'm just using this as an example because it's a tetrahedron people can kind of imagine in their heads. But it might be 8 that actually give us the most efficient way to crush everything that's in the center, right? But once we had this conversation with him, he basically said, okay, this fixes most of our problems. If this will work correctly, then yes, you will be able to get to where you want to without hitting the massive temperatures and the pressures that you need. Because again, I don't need high temperature or high pressure if I'm controlling the distances with space-time itself. And even better, once you get that first generation up and running, just like I said with James Watt's engine, cool, we have the first generation. Take that data, go back to the computer, run all the simulations again, second generation, third generation, so on and so forth.
So these experiments, they're fusion plasma simulations. So they're in a computer. So you're not. I had visions of like some lab in the middle of a desert, like a bit like CERN, like smashing things together.
So he is doing some of that work. But not a lot because he's waiting on the warp bubble itself, and that's Dr. Chance's work. Dr. Cassaberry's work, on the other hand, is going because he's already running a fusion lab, so he's already doing fusion. He's collecting data for his program to make his program better. So when Dr. Glenn comes and says, "Here's the physical properties of the warp bubble," he can plug that in to get better numbers for how to create the fusion reactor. That's his idea.
So what? Amazing. So when you and I'm sure there's other companies looking at this, because the idea of really with the idea of a sort of limitless power, that seems like a sort of holy grail of physics, really.
Well, it is, and that's what's really bizarre. In fact, that's what stopped me from incorporating the company at the beginning, because it was in physics. There's 2 massive fields. There's quantum and there's relativity. Quantum mechanics covers 3 of the fundamental 4 forces. It covers the electromagnetism, the weak force, and the strong force. Cool. It's also very small. Quantum covers the microscopic, the quantum level. And no, not Ant-Man. Stop that. The relativity, on the other hand, covers gravity, covers gravitation. Gravity is the weakest of the 4 forces. It is almost non-existent. Keyword being almost. The only reason that we even see it exists is because it never drops to 0, and it extends to infinity. So it's almost 0, but gravity, when you're looking at astronomy, that's the only force that really matters, right? The problem is that the math of quantum doesn't work in relativity, and the math in relativity doesn't work in quantum. So you can't really combine them as of yet. We know that there's probably a way to do it, we just don't know how to do it yet. So if you get a PhD in relativity, why would I look up quantum stuff? If I'm getting a PhD in quantum, why do I look at relativity stuff? So the people who are doing the warp drive literature, doing the space-time distortion stuff, are looking at relativity. They're thinking big. So they're looking at R equals 100 meters. People who are doing quantum stuff are thinking very small. Why would they be looking at gravity? Gravity doesn't matter at that scale. So I said, well, why can't you just do one or the other? And of course, the quantum people couldn't discuss the relativity, and the relativity people couldn't discuss the quantum. I mean, sure, they knew enough to like have the conversation, but not like the deep dive, right? So when I called these people and I'm like, what are you doing? Like, I literally pulled out actually, I think I got a stack of it. Hold on, I'll see if I can find it. There we go. So what I did was I actually downloaded every single warp drive paper since 1994.
That's a big stack of them.
But it's not. When you think about it, since 1994, that's it. That's not a big stack.
Oh, I see. Yeah.
That's not a big stack. There's like maybe 30 people who've written on this in the world. So I reached out to them and I said, have you looked at this? They're like, why do we do that? We don't need to build a small one. We want to build FTL. Cool. You're not going to get FTL tomorrow. So can you build it small? Well, I mean, I guess you could, but why would you? Don't worry about it. And I looked everywhere. And as I said beforehand, yes, a lot of people are doing fusion, but they're doing it the tokamak style, or they're doing inertial confinement. No one's looking at what we call gravity assisted. And it's bizarre. In biopharmaceuticals or biochemistry or biotech, you always look at the natural system first, right? Because you want to use a natural system. Perfect example is vaccines. Why should I create a new immune system when I can just trick your immune system into doing it for me? You always want to do something easier, especially if nature's already given you a scaffold. Well, walk outside and you'll see the best fusion reactor in existence right now. It's the sun. We realized, and the sun's a big gravity bomb. Gravity's pulling everything in, and the fusion reaction is pushing things out, but it's an equilibrium. In fact, near the end of a star's life cycle, that's when it becomes a red giant, it becomes a supernova, or things like that, right? So it's a big, slowly burning fusion bomb. Why can't we do that in a really small way? Why can't we do it that way? No one ever asked that question. No one else is doing what we're doing because no one saw the connection between space-time distortion and fusion.
Amazing. Well, I think the transformative potential of quantum space-time distortion and potential interstellar space travel is obviously amazing. Say you had some of the leading billionaire space tech entrepreneurs listening to this podcast, Elon Musk, Jeff Bezos. If you had their ear and they would write you a check for however much you wanted, $10 billion, whatever. What would you do differently? Is it the sort of thing you could speed up 100-fold, or does it need to sort of stack up as the collective knowledge of the subject increases?
So it's funny you should say that, because I wouldn't ask them for $10 billion because then they'd own me. I'd ask them for about 50 million for phase one, because right now adding more labs would be good, but there's a limit because you can only hit this from so many perspectives. Like, you're not using, let's use vegetable oil. Like, no, there's only a certain number of paths to get to this kind of quantum space-time distortion. We could add a few more labs, certainly, but until we actually do it in the lab, having 20 labs doing the same thing isn't going to really help. It's not going to do it. You might have some duplication, and don't get me wrong, I'd love to add, the goal right now is to add like maybe 3 or 4 more labs, and each of them doing kind of one's attacking from a magnetic perspective, one's attacking it from an electronic perspective. Like, there's different methods to use, and I'd like to add a few more, but like having 50 labs working on this is not going to make it go. Now, once we get past proof of concept, then I need 500 million, because now we can take that and begin building the microfusion reactors. And the way that we've designed it is we've basically got like a hub and spoke model. The hub is we have a central hub, which is my chief science officer, Dr. Athena Ivanov, who's got an MD and a Ph.D. in quantum chemistry, and she just finished her NASA fellowship, so she's brilliant. She's going to, part of that 50 million we use to build our own lab. But right now we have nothing to study in that lab because we haven't done any of this stuff yet. As time goes on, the people in the other labs, you have PhD students, you have postdocs, they are going to be looking for jobs. Come our way. We're going to build feeder mechanisms to have them come to us. And we're going to add more labs as time goes on, but we're going to also build up our main lab as well. So we're going to have a main lab, satellite campuses, things like that. It's a hub and spoke system. But you can only have so many spokes before, one, you can't coordinate anymore. People are duplicating their work. This is a problem that you can throw money at, but it's a curve. Once you hit a certain amount, cool, that's great. Let's all buy Corvettes, but it doesn't really matter past a certain amount of money. We just have to keep pounding away at it. The good news is that's cheap. $50 million for proof of concept. We budgeted that for 5 years. Everyone's getting paid relatively well. No one's going to become a billionaire or anything like that, but everyone will be taken care of. $50 million for 5 years is a pretty decent deal considering the billions of dollars that have been thrown to fusion over the past few years. Now, once we show proof of concept, yes, we need $500 million to begin actually creating our fusion facility and things like that. But that's still really cheap. And once we have proof of concept, now I go to the oil companies and the energy companies, because they're the ones who are investing in fusion right now, because they know, stop burning oil, climate change is a thing. You can either give me money, or I'm going to go to your buddy down the street who will give me money, and then I'll run you out of business. It's your call. So for us, it's just getting to that phase one. So if these billionaires who are listening were sitting down and saying, how much do you want? I'll give you the budget, $50 million for 5 years. That's it. That's all I need from you. And I would, of course, negotiate them down to as small amount of equity as I possibly could for obvious reasons. But yeah, it's not, I wish that I could just throw billions of dollars at it to make it happen. But that's not the way it's going to work. What's going to work, and this is where kind of like my my background is. My PhD is in political science, and people kind of go, "What are you doing? How are you doing this?" The answer is, it's just like building a private state. That's what a corporation really is. So my superpower is slotting the right people in the right places, seeing where the gaps are, and filling those gaps. Once you fill the gaps, I don't need anything else. In fact, I don't want to go on those hiring binges of like, the startups who get a bunch of money coming in. We're going to hire 300 people. Why are you doing that?
Yeah.
I'd rather have the 10 people I actually want and need and who fill those gaps that I know I have. Like I said, I need a lab that can do X. I need a lab that can do Y. Find me 3 of those. We'll pull one of them on board, maybe 2, because maybe they're doing, just because you're using electricity, you might be doing electrical charges. You might be doing something a little different. Cool. Bring them on board. I don't need 60 labs. There's no point in that. The idea behind the setup was Manhattan Project meets Bell Labs. We have a specific goal. We know where we want to go, but I want to give you the freedom to go into the lab and mess around a bit because you never know what you're going to find out when you go a little bit off the beaten path, right? And 60 labs ain't going to do that. It's not. So right now it's just we got 3. I like to add 3 to 4 more, so it'd be 6, 7, maybe 8. That's it. And people kind of go, just like you said, why so few? This stuff is weird. Not many people get it. Just throwing money at a bunch of labs who have no idea what they're doing, that's just a waste of money. So we vetted every single lab or researcher that we've talked to make sure that they understand what's going on and understand what's happening, because those are the ones I need. Just because, picking up a fresh PhD or a lab that's been doing fusion power for 20 years, that doesn't mean they're going to be able to use this stuff. Because it's such a new technology, you got to curate it correctly, and that means it's a very small pool to pull from.
It's fascinating. Well, look, it's been so great to chat, and what I like about what you're doing is it's so, it's ambitious, and I think, you look at how quickly technology and humanity sort of innovated between the first powered flight to the landing on the moon over a few decades, and then there has been a sort of relative dry patch where most innovation has been through computing as opposed to technologies. And I think, hopefully the next couple of decades we're going to see a lot of quote unquote crazy physicists and creatives and innovators just daring mighty things. It's one of those sort of throwaway things people say, but actually, we don't know unless we try.
Right.
And I love the ambition of it. I think it's fantastic.
It's funny that you should say that, because I think the computing revolution is very much what we're doing as well. Everyone wants bigger rockets. Everyone wants bigger spaceships. We're going the exact opposite direction. We're going smaller, just like the computing revolution was. If you remember from the 50s, they're like, you're going to have a computer the size of a building, and it's going to do all this stuff. And no, that was not the revolution.
Quantum, yeah.
The revolution was going smaller. The example I always use is, hey, here's something that we all have in our pockets that has more computing power than the entire U.S. space program combined, times like 100. It's ridiculous, right? But we might still fail. Just because we know it's theoretically possible doesn't mean that we have the engineering and technical expertise to do it. And anyone who I talk to when it comes to investing in anything else, I'm very blunt about it. We might fail. With that being said, the chance to fix climate change and the chance to give humanity the stars, even if it's a 5% chance, wake me up in the morning every morning. That will get me out of bed every single time. And yes, there's a high risk of failure. And again, I don't know. Someone actually asked me, what are the chances? I said, between 0 and 100. How in the hell am I supposed to know right now? We don't even know enough.
At least you're honest. Yeah.
Well, I refuse to take someone's money when they're like, so you can do this in 3 years. Oh, yeah, sure. No. I'm not going to build an organization around lies. I always tell people up front, listen, we know it's theoretically possible. We're going to try for 5 years, and we might go outside for 7. If we can't do it in like a decade, we got to get back to the drawing board and figure out what's missing from this. Because I don't want to fall into the fusion trap, because, fusion reactors have been around since the 60s. Well, they've been around. And fusion's always 10 years away, isn't it? Always 10 years away. And so for me, I'm like, look, if you've been doing the same thing for 60 years, maybe you should try something else. And here we are.
Greg, it's been great to chat to you. Thank you very much.
Thank you so much, Ben. I very much appreciate it. Thank you so much.